Okay, so let's do a basic example. We know if this is a circle of radius 3, we know that the total area is pi r squared, so it's going to be 9 pi, so this should just be a quarter of that, so 9 pi over 4. Let's see how we can show this, or think of this in terms of double integral, just to practice before we move on to double integrals that actually have volumes or other integrands other than just dA. Okay, so if we wanted to evaluate this, we're going to switch to polar. And we just showed on the previous page that in polar, dA becomes r dr d theta. Then we're going to set up our limits. So if I'm starting with r, my inside limit, I'm going to now think of freezing theta, and I'm going to shoot an arrow radially outwards for a fixed theta. And I'm going to think of where does that arrow enter the region and where does it exit. So it's just entering when r is 0, it's exiting when r is 3. And then I'm fanning that arrow like a little sprinkler over my whole region r, and I'm saying what's the smallest theta that I could have chosen to shoot the arrow, and what's the largest. And the smallest theta is going to happen when theta is 0, and the largest is when theta is pi over 2. Now I can actually just do this double integral. What's nice, if you notice, is I can do a little shortcut. I can either do it the normal way, or because my bounds are all constants now, and I can think of this as just a function of r times 1, I can actually decouple this double integral if I'd like to do it even faster. So if you remember, we've shown you can decouple. In this case, I'll just do the theta part. And I'll just let the theta part be 1, and this part is just r dr. And that's going to be really fast because this integral is just going to evaluate to pi over 2. And this one's going to be r squared over 2 from 0 to 3, which is going to give me 9 halves. And we get back to what we knew from geometry, which is 1/4 of the total area, 9 pi over 4. Okay, so that was just a basic example to help you see how we would do it just with an area. And now let's think about in general, if I'd like to set up the double integral in polar coordinates with any type of integrand. So let's say I'd like to rewrite this. I have it as a starting point in Cartesian coordinates, and I'd like to rewrite this in polar. First, I'm going to rewrite dA as r dr d theta, and then I'm going to convert the integrand to polar. So in polar, we know that x is r cosine theta, y is r sine theta. So we're just going to substitute that. And then we need to figure out how to find our limits. So let's suppose we're going to do the ordering dr d theta first. In that case, we're imagining we're fixing theta, and we're going to draw an r line radially outward from the origin, just like we did above. So let's just show an example. The lower limit is going to be where it enters the region. And so in this case, you can see that will be a function that depends on theta. So we'll put that down below. R down here would be h. I'm calling it h sub 1 of theta. And then the upper limit is going to be where that would exit the region. In this case, that'll be h sub 2 of theta, some other function of theta. And let's also fill in what we just wrote above. Our integrand becomes in terms of r and theta, and then we have our dA becomes r dr d theta. All right, and then your smallest, or your theta limits are still always going to be constants. Your outer limit, in this case, this is theta, it's always going to be a constant. And it's going to be the largest and the smallest theta values in this region. In this case, I just wrote it as alpha and beta. There. Okay. So that's if we wanted to do the ordering dr d theta. We could also go the other way around and do d theta dr. So let's think about what that would look like. So using the ordering, and let's actually draw another example here. So in this case, I'm just going to draw a little segment where it's kind of easier. Maybe we've got something like this, and maybe we have something like this, and then I'll give us some regions here. Okay. And let's shade this in. This is my region R. And now what you're noticing, if I'd like to do it this way, I need to think of theta along here as a function of R. And I'm going to write this side as another function of R. And this is my region capital R. Okay, so if I'm using the ordering d theta dr, now I'm fixing R and I'm drawing these theta curves. So if you're thinking of, we're chopping up our region with a knife, when I am integrating first with respect to theta, my knife now is going to go along curves of constant R. So let's imagine, right, these are curves of constant R. And so I'm going to start getting my knife doing things like this. Okay, so let's just pick one of those here. And right, I'm calling these theta curves. So the lower limit is going to be where this theta curve enters your region. In this case, this is coming from what I'm calling this g sub 1 of R. This will be a function of R. And then the upper limit will be where it exits the region, which I'm calling g sub 2 of R. And then my smallest, now it'll be my R limits that are constants. Whatever is your outer integral will be constants. And I just want my smallest and my largest R that bound this region. And so you can see the smallest radius that I could have in this picture is here. And the largest one that I can have is coming from this furthest out piece. So let's call this smallest R, we'll call that alpha right there. And this largest one, we'll call that beta right there. So alpha to beta. Now, I understand this probably looks really crazy. I'm about to show it with a specific example, so I think you'll be okay in a minute. But just wanted to give you the general idea before we jump in. Okay, so let's look at a couple specific examples next.